Okay, my amazing AP Chem students. So, last class, maybe the time before, depending on when you're watching this, we talked about neutralization reactions when acids react with bases and we get water and an ionic salt. And then we were looking at the pH of those mixtures. And we would use a BCCA table to figure out what we had excess of. Either we had excess of a strong acid or a strong base, or we had excess of a weak acid or a weak base. Now, for this example, and probably the least common occurrence is when we don't have an excess, when we have the perfect amount of moles of acid and moles of a base. So here I see that I have 30 milliliters. In your notes, if you're wanting to follow along, I'm on page 29 in our Unit 8 packet. So a 30 milliliter sample of 0.5 molar acetic acid, CH3COOH, is mixed with 30 milliliter sample of 0.5 molar sodium hydroxide. On the AP test, it's not going to say write the net ionic, and so this time we're going to use the net ionic. As soon as you can tell that it's the same moles of acid as moles of base, then I want you to stop and be like, oh, there's not going to be any excess, and then it's a lot easier if we use the net ionic instead of the full reaction like we have been doing. Okay, so I might start setting this up, and I'll do pencil. Okay, so if I was a student, I'd be like, okay, I'm taking an acid and I'm taking a base, and I'm going to put them together and I'm going to find a pH. Well, I better use a Becca table to see if I have any excess. And so we're going to have our acid, CH3COOH, aqueous, plus our strong base, so weak acid, and then sodium hydroxide is a strong base. And that's going to turn into water. And then salt. Now, we know the water came from this hydrogen and that hydroxide, and so we're going to get sodium acetate, CH3COO. Sodium is soluble, and we haven't really gone over it in class, but acetate, the CH3COO minus, is usually quite soluble as well. But sodium definitely is, and so we got aqueous, okay? And we have our BCCA table. So I see a volume and I see concentration, and when I multiply those together, I'm going to get the amount of moles. So if I have 0.300, 0.0300 liters times by 0.50 molarity, then that's going to be 0.015 moles. Okay, so 0.015 moles when I took my volume in liters and times by my concentration, so I get 0.015 moles of my acid. Now, I'm just noticing, oh, look, it's the same volume and same concentration. So it's the same volume and it's the same concentration, so I have the same amount of moles. 0.015 moles. That means if I have the same amount of moles and there's a 1 in front of these, I don't have a limiting or an excess. I have a perfect combination of these things. So when that occurs, I'm going to want to do my net ionic instead of this full reaction, and we'll see why here in just a moment. So I'm going to show you this. You don't need to write it down. But we had our weak acid, we had our strong base. We had it turn into water, liquid, and then the salt was sodium acetate, and we talked about why that one's aqueous. When it's a weak acid or a weak base, we don't break them apart into their ions. So this stays as CH3COOH, aqueous. But when it is a strong acid, or in this case a strong base, then we do break it apart. Na plus aqueous and OH minus aqueous. That will turn into water. Now when it's a liquid or a solid, we don't break it apart. And then when it's an ionic salt, if it's soluble, then we break them apart into their ions. So this is going to be Na plus aqueous and acetate CH3COO aqueous, and it's a minus. Okay. We have a spectator ion, and that spectator ion is sodium. So the net ionic for this reaction is CH3COOH aqueous plus hydroxide aqueous turns into water, liquid, plus acetate ion CH3COO minus aqueous. Okay, so I'm going to go back and I'm going to update this. So instead of it being NaOH, it's just OH minus, and instead of it being NaCH3COO, because remember, Na was our spectator ion. I'll move all of it over. So now this is going to be CH3COO minus aqueous. These are our reacting species, okay? Okay, now that I've updated that, I'm going to go back to my pen. Because this is a strong base, the moles are equal to the moles of hydroxide. So since we had 0.015 moles of sodium hydroxide, we also have 0.015 moles of hydroxide. So then we can keep going. Starting off with 0. Our reactants are going to be minus. Our products are going to be plus. So we get 0.015 minus X, 0.015 minus X, X, and X. And like we've been seeing, X is equal to 0.015 in both situations. So that means that both reactants we completely consume for this reaction. And we're left with 0.015 moles of water that we produce and 0.015 moles of this acetate ion. Okay? All right. Important. Becca tables, BCCA tables, are only moles. Only moles. And it's important that we remember that in our BCCA table, because guess what? Here in a little bit, we're going to do an ice table. And in ice tables, it's almost always concentration like molarity, but it can be pressure, atmospheres, torrs, those kinds of things. But in this situation, it's going to be molarity, moles per liter. Okay. When you do your BCCA table and you go, guess what? I don't have any excess. Your next step is to take what you do have, this conjugate base, because there's the acid, that's the conjugate base, and see how this is going to influence the pH. Okay? Now, because this is a base, right, a conjugate base, we are going to need our Kb instead of a Ka. So up above, it tells us what Ka is. right here, says Ka is equal to 1.8 times by 10 to the negative fifth, and we're solving for Kb. And if you look at your reference paper, I'm trying to see if I have one close by, under the equilibrium section, it tells us something really interesting. It says Kw, although it's equal to these things, it's also equal to Ka times by Kb. So Kw at 25 degrees Celsius, which this is at 25 degrees Celsius, is 1 times by 10 raised to the negative 14. We're solving for that Kb. So Kw equals Ka times by Kb. So Kw divided by Ka will equal Kb. So we'll do our 1.0 times by 10 to the negative 14 divided by our 1.8 times by 10 to the negative fifth. Okay. So we have 5.55 repeating times 10 to the negative 10 for our Kb. 2 sig figs here, so we're just going to keep track of that. 2 sig figs. Nice. There is one other item. Oh no, that's later on. Okay. So now that we know that other than the water, the only thing we have in here is this conjugate base, and we solved for the Kb, we're going to see what's going to go on with an equilibrium reaction of this conjugate base. So this base can react with water, and that can produce the weak acid and some hydroxide. Okay? So when we have some conjugate base, then it's within the water, and so a small amount of it can react and produce the weak acid and hydroxide. Okay? We are going to be adding into an ice table. Now I'm going to tell you right now, the most common mistake that I see students make is they want to take this 0.015 and put it right into the ice table, but this is moles, and we need this to be molarity. Okay? So, concentration initial of this CH3COO minus, that's going to equal the moles of it, 0.015 moles, divided by the additive volume. So our 0.030 liters plus our 0.030 liters. Okay, so when we run that number, .25, and that was 2 sig figs. Okay, we have 0.25 molarity. So we are starting with 0.25 molarity. Water is a liquid, and so we don't have to include it in the ice table. We do include it in our BCCA tables, liquids and solids, but not in our ice tables. Then we're starting with 0 of our products, and we got minus x plus x plus x, and then 0.25 minus x, x, and x at equilibrium. Our Kb number is times 10 to the negative 10. So this is of a magnitude that we can make that exception that we've talked about in class. Okay, wonderful. My goal right now is to figure out, when this conjugate base is in water, how much hydroxide is produced. Because once I know how much hydroxide, I can get POH, and then I can finally end with pH. So I'm going to solve for X so I can get that concentration of hydroxide. So Kb is equal to products over reactants. Okay. Okay. Now, this is the same as x, x, and then 2.5. So Kb is equal to x squared over 2.5. So 2.5 times by Kb square root is equal to x. All right, so (2.5) times by Kb raised to the 1/2. X is equal to 0.000037. This is not my moles of hydroxide, it is my concentration, molarity, moles per liter. So I can figure out pOH really simply because pOH is equal to the negative log of the concentration of hydroxide. So I'm just going to do negative log of that number. Okay, now, we've been kind of tracking our sig figs throughout here, and we lost track a little bit. To me, I'm seeing a Kb that was 2 significant figures and a 2.5 that was 2 sig figs. So this was 2 sig figs. So when concentrations are 2 significant figures, then pHs or pOHs are 2 digits after the decimal. So 4.42867, but recognizing like 2 digits after the decimal. So pH is going to equal 14 minus pOH, 14 minus that number, and I'm going to keep that 2 digits after the decimal. So my final answer, 9.57 is my pH. This is a reasonable number because after these two items reacted, we were left with a conjugate base, and so it would make sense that our pH is higher than 7 at 25 degrees Celsius. Okay. All right, everyone. Please, if you need to, go through this video again, step by step, and in the problem set, the question that correlates to this one is number 11. Number 11 on page 39. Okay, so I'm sure you already have the key, but I'm just going to quickly put it up here so you can see it. But it is the same idea. We start with a BCCA table. We find out like, oh, guess what? I don't have any excess. And so then when I do that, we see what was left. And so there was a conjugate base item. Because see, there's the acid. There's our conjugate base. Okay. And then we use an ice table to see what's going on with that conjugate base. I calculated a Kb, and I figured out how much hydroxide was produced because of that conjugate base. From there, I solved for a pOH and then my pH. Okay, wonderful. If you can, join us for lunch so that we can walk through this together. If not, you have the video, and I want you to get this page 39, number 11 done. All right, see y'all. Have a great day.